All right, so we'll take a look at some additional problems from the gases module. And now we're going to take a look at applying Boyle's law. So remember, Boyle's law is the PV relationship. And it goes P1 V1 equals P2 V2, where the ones here just represent what you have initially for the pressure and the volume, and then the twos here represent your final conditions. Okay, sometimes this is written as PI VI, where the I's just mean the same thing, initial, and then PF VF, where the F's just means final. So either I versus F or 1 versus 2, we're comparing initial and final conditions. So a couple pieces of information we're given here. We're told that we have a gas storage cylinder. And then they give us the dimensions of this. So it's 4.7 centimeters wide. And then it's 19 centimeters high. Okay, so if you think about a cylinder, kind of looks like this. Okay, so the height here is 19 centimeters, and the width, which would be the diameter in this case, is 4.7 centimeters. So what we can do, you can use those dimensions to eventually calculate the volume, because Boyle's law does deal with volume. Let's see what else we're given. So it says the contents. This contains nitrogen gas is in here. And we're told that the pressure is 24.5 atmospheres. Okay, that's all the information that's given. It says if the cylinder is open and the gas is allowed to escape. Okay, so let's say the gas leaves now, exits the cylinder into a large empty plastic bag. I have a bag here collecting all the gas. What would be the final volume of nitrogen gas? So what then would be the volume of this bag that we're looking at, including what's collected in the plastic bag, and what's left over in the cylinder. Write your answer in liters. Make sure your answer has the correct number of significant digits. Okay, so a couple of things we want to identify here, what we're given, and then what we need. Okay, so we're given the initial pressure. Let's see here, we're given the pressure as 24.5 atmospheres. Then we're given the volume as, let's see, what's the volume? Well, we're not given the volume, we're given the dimensions of the cylinder. So we can use those dimensions to calculate the volume. So what's the formula for the volume of a cylinder? Well, if you don't remember, over here on the right side of your ALEKS page, you'll see there's a little tab that says data. If you click on it, you go down to volume formulas. You will see, hopefully, there is the formula for the volume of a cylinder. So the V volume is equal to pi r squared times height. So pi r squared times height, where r is the radius, h is the height of our cylinder. So the h here is going to be 19 centimeters. The r, the radius, is just simply the diameter, or the width, divided by 2. So if the width here was 4.7 centimeters, 4.7 divided by 2 would be 2.35 centimeters. That's your r. Okay, so we can use that formula to calculate the volume. So we have pi, which you can plug into your calculator. We have r, that's going to be squared, and then we have our h. Now we want to keep in mind the units that we're dealing with in this problem. So the units are going to be important as we do this. So we have now our dimensions. So our r here is going to be 2.35 centimeters, and then that's going to be squared. And then we have our height, which was, what was that, 19 centimeters. So if we plug that in your calculator, what we have is we have pi, let's see here, times 19, and then times 2.25. Okay, so that's giving me 329.6. And then that's the unit now is cubic centimeters that we have. So if you'll notice here, our we need the answer in liters, so we can convert this volume to liters right away. You have 329.6 cubic centimeters. If you remember way back from your metric conversions, 1 liter is 1,000 cubic centimeters. Divide by 1,000, so we end up with 0.3296 liters. Now, in this calculation, our volume, our height here was 2 sig figs, our diameter was 2 sig figs. So really, this should have 2 sig figs, but we're just keeping extra significant figures or extra digits so that we don't round prematurely. So this is my initial volume that I've just calculated. The initial pressure P1 was given as 24.5 atmospheres. Okay, so those are our initial conditions. So what are the final conditions of pressure and volume? Well, final pressure, P2 here, it says that it's allowed to escape into a large empty plastic bag. So we can assume then that if this goes into the empty bag, the pressure is going to be whatever atmospheric pressure is, which is going to be 1 atmosphere. So then our V2, the final volume, is what we need to calculate. So if I have my P1, V1 is equal to P2, V2, and I need to solve this for V2, well, if I rearrange my equation, V2 will be equal to P1, V1 over P2. And I'm going to substitute my values into this equation. P1 is 24.5 atmospheres times V1, which was 0.3296. So 2 sig figs to keep track of. And then our P2 was 1 atmospheres. I can solve this equation for V2. We can stick that in our calculator. Let's see, we have 24.5 times 0.326, and that's divided by 1. Okay, so that is giving me 8.0752 liters, could be my unit because the atmospheres cancel away, is my V2. How many sig figs should I have? Well, I had 3 sig figs here. This one should have 2 sig figs. Our atmospheric pressure, assuming, is an exact value. So our final answer then should have 2 sig figs. This would be 8.1 liters as my final volume, the total volume of nitrogen. So in different versions of questions like these, you may be given a different container. So in this case, we were given a storage cylinder. So we were able to use the formula for the volume of a cylinder, which is given here. Now you may be given the the container being a cube or a prism. In this case, we can use this formula, or if you're given the a spherical container, we can use a 4/3 pi r cubed, or a cube, for example. It would be these formulas. So depending on what information you're given, we can use the most appropriate volume formula to calculate that initial volume, and then applying Boyle's law, we solve for the one unknown in that problem. All right, so in this question, we're looking at using the ideal equation of state, or the ideal gas equation. And that's probably the most important gas equation that you'll see. So the equation goes PV is equal to N times R times T, where P, as we've seen before, is going to be our pressure. V is going to be the volume. N is the amount of the gas, which is typically in number of moles. T here is your temperature. And remember, whenever you see temperature in a gas law equation, this needs to be in Kelvin. And then R is the gas constant. And there are different values for the gas constant that you'll see. You want to use the most appropriate one depending on the units that you see in the question. So if we go to data, we can see down here some of the constants. You can scroll down. And for the gas constant R, you'll see that there are a couple options. So we have one here that's 0.082 liter atmosphere per mole Kelvin. So if we're given the volume in liters, pressure in atmospheres, amount in moles, we can use that one. Or we're given another number or value for R, and the units are slightly different. So you want to use the most appropriate unit or value for R. In most cases, it's going to be the 0.0821 liter atmosphere per mole Kelvin. So in this type of problem, as with any gas law problem, you want to organize the information. Okay, what are you given? And then what do you need? So in this problem, we're given the temperature at 25 degrees Celsius. Okay, that's your T. Temperature needs to be converted to Kelvin, so do that right away. Don't wait until the last minute. To convert to Kelvin, we're just simply going to add 273 to the Celsius temperature. So that gives 298 Kelvin. That's your temperature. We're given the amount of the dinitrogen monoxide gas as 686 m-mole. That means millimole. That prefix M there means milli. So we can convert that to regular number of moles by doing a metric conversion. Milli means the same thing wherever you see it. For every 1 mole, there's 1,000 millimoles. So we just divide that by 1,000. We end up with 0.686 moles. So that's our N. So the 298 Kelvin, that's our temperature. This here is our N. It says calculate the volume. So right away we know V is going to be our unknown. That is collected. And it says to assume that the pressure in the room is exactly 1 atmosphere. So P is equal to 1 atm. So in our equation, our ideal gas equation, we know, or we're given pressure, we're given the amount N, we're given the temperature T, R is a constant, so we're always given what that is. So we need to solve this equation then for the one unknown, which is going to be our volume. So we want to rearrange that equation to solve for V. So we can manipulate this around, do a little bit of mental gymnastics on it. So let's write this PV equals nRT. We're going to solve for V. So if I isolate V on one side and move the P on the other side, I need to now divide the right side by P. So I'm going to substitute the values that I just found or that were given in the problem. So my N, number of moles, was 0.686 moles. My ideal gas, or the gas constant, right? So if you remember back, we can go to the data to find that. We want to use the one that has liters and atmospheres and moles and Kelvin in it, because those are the other units that we have. So it's 0.08, 0.082, 0.574. And then our unit here, a liter atmosphere per mole Kelvin. And our temperature was given as, well, we found that as it was given in Celsius, we converted it to Kelvin, 298 Kelvin. And then our pressure was just exactly 1 atmospheres. So I'll just substitute that into the equation, and then we just solve it. So looking at the units now, we can confirm that we use the correct value for R. Atmospheres cancel up here, moles cancel down there, Kelvin cancels up here. The only unit then left is liters, which makes sense because I'm trying to find volume, and liters is an acceptable unit for volume. So we'll plug this into your calculator. We have 0.686 times 0.082057 times 298 divided by 1. All right, so we want to round this to the correct number of sig figs. We have 3 sig figs here. We have more than 3 sig figs on this. We have 3 sig figs there. We're told that the pressure was exact. So then our final answer then should have 3 sig figs. So if we round our final answer to 3 sig figs, or if we just write out all the digits, so we get 16.7741 dot 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 dot, and then the unit here is liters. We're going to round this to 3 sig figs. Those are the first 3. Next digit 5 or above, we round 7 up. We end up with 16.8 liters as the volume of the sample of dinitrogen monoxide. Let me just double check. Yes, 16.8 liters. So with the ideal gas equation, PV equals nRT, we can look at the information that's given in the question, and then from that we can identify what the one unknown is, because there's only going to be one unknown in this equation that we need to rearrange and solve it for. When we insert, when we convert, when we use those numbers, those values in here, we want to make sure that they have the correct units that correspond to the units for R, for example. And again, R is a constant. You don't have to memorize that. You'll always be provided with it if you need it. And you can look it up here in ALEKS in the data on the right side. So really, if you think about it, most of the gas law problems really just kind of boil down to just applying math to these gases, this physical state, and some of the properties.